everyone, welcome you all. So in this part of the video, which is the fourth part and the last part of the chapter real numbers, we are going to see the solutions of problems from exercise 1.2. Okay, so let's start with question number 1. What it says prove that root 5 is an irrational number. Okay, so to prove root 5 as an irrational number, here we use contradictory method. Okay, contradictory method means method of contradiction. Contradiction means we will be assuming something which is just opposite of irrational number, and you must know that all real numbers are actually divided into two parts. One part is rational and another part is irrational. Okay, and you must know this thing that a number which is rational can't be an irrational, and a number which is irrational can't be a rational number. The world of these two types of numbers are completely different. Okay, a rational number can never be an irrational, and an irrational number can never be a rational number. Okay, so we use this contradiction. Okay, let's see how to solve. So first of all, we'll be assuming that a square root of 5 is an irrational number. Okay, and the process of assumption will be like this. Let a square root of 5 is a rational number, just opposite to irrational number what we have to prove. Okay, so what we have assumed that root 5 is a rational number of the form p by q, where p and q are co-primes. Co-primes means p and q are not having any common factor. What that means, let us assume with an example, like if we have a fraction like 6 upon 8. Okay, it's a rational number, but here you can see that 6 and 8 are having a common factor too. That means this fraction can be simplified. 2 3 is 6, 2 4 is 8, so we are getting 3 upon 4. Now this 3 upon 4 can't be simplified any further. Why? Because now these are having only one common factor, and that's 1 only. So if we divide by 1, then still the number will remain the same, 3 upon 4. It means this is the simplest form, or you can say lowest form, which can't be simplified any further. Okay, this is the simplest form, and this 3 and 4 are co-primes. The pair of numbers, what are co-primes? The pair of numbers which are having only one factor, that is 1. Or in another way, you can say that there is no any factor. So our assumption here is that p upon q are co-primes, means they can't be simplified any further. Okay, so this is our assumption. So we can write, that is p upon q equals a square root of 2. Okay, as per our assumption. Now in the next step, we take a squares of both the sides, LHS and RHS, a square of LHS and a square of RHS, and here we'll mention squaring both sides. So after squaring, what we are getting? We are getting in LHS we are getting p square upon q square, and in RHS root and square root will get cancelled and we'll be getting 2. Okay. Now transpose this q square to RHS. It will become 2q square. Okay. That means p square is divisible by 2. Okay, as you can see that what we have got here, that 2 into q square is equals p square. That means 2 is a factor of p square. That means 2 will divide p square, and if p square is divisible by 2, that means p is also divisible by 2. Okay, this we have understood or we have seen in third part of the video where we have proved a theorem. Okay, and if you have forgot or if you have not seen that video, then let us see a small example of this. Like if there is a number 6, okay, then 6 is having factor 2 and 3 other than 1 and 6. Okay, the prime factorization of 6 is 2 into 3. Okay, now if you will take 6 square, then what we will be getting? This square of 2 into 3. What does that mean? 36 equals 2 into 3 into 2 into 3. Okay, so and this also relates with fundamental theorem of arithmetic, like uh, whatever be the power of the natural number, which is a composite number like 6 here. 6 is having prime factorization 2 and 2 into 3. Okay, when 6 can get divided by 2 and 3. Okay, both. And if 6 is getting divided by 2 and 3, then whatever be the power of 6, the number which is power of 6, power 6 power 2 or 6 power 3 or 6 power 4, what will happen? We will be getting only these numbers 2 and 3 as their factors. So you can see here that 36 is divided by 2 or divided by 3. Okay, and 6 is also getting divided by the same factors 2 and 3. So simply take this 36 as p a square. Okay, as 36 is a square number. Okay, so if you are taking 36 as p a square, or you can say as 36 is a square of 6, so simply consider this situation. At the place of 6 we have p. So so since p a square is getting divided, means we have two factors, one is 2 and another is q a square. Okay, so if p a square is getting divided by 2, as 36 a square of 6 is getting divided by 2, then 6 is also getting divided by 2. 6 of a square of 6 is getting divided by 2, so 6 is also getting divided by 2, and therefore since p a square is getting divided by 2, so p a square, sorry, p will also get divided by 2. And here we'll have some factor, some other factor, we don't know what, but there will be some factor. Okay, so we'll be following the same conclusion or the same theorem which we have proved earlier. So here we have got that p is divisible by 2, that means 2 is a factor of p. Okay, now let's move ahead. Since now p is divisible by 2, so we can assume that let p equals 2 into some factor. We don't know what will be the factor, so simply assume any variable. Let it is m. Okay, now in the next step, again a square, take a square of both sides. Okay, squaring both sides. Now at the place of p square we can write 2q square from here. So we are considering this equation as equation 1, and we are using this equation to replace p square by 2q square. So at the place of p square we can write 2q square, and in RHS we are getting 4m square. Okay, square of 2 will become 4 and m square. Okay, now transpose this 2 to RHS. So here we'll be getting q square equals 2 will come to RHS, and we will divide this quantity in RHS, and this 4 will get divided by 2 and will become 2. Okay, so we are getting 2m square. And you can see here, as we have concluded here from this equation 1, that 2 is a factor of p square. That means p square is divisible by 2, and so p is divisible by 2. In the same way, here we can conclude that q square is divisible by 2, and so q is also divisible by 2. Now simply recall that what assumption we had taken. Okay, and before looking into that assumption, here what we have got, one, we have got that p square, sorry, p is divisible by 2, and here at last we have got that q is divisible by 2, means p and q both are divisible by the same number, that is 2. Okay, that means 2 is a common factor of p and q. Okay, but if you'll see our assumption, what we have assumed, that P and Q are co-primes. That means they are not having any common factor. Okay, and here we are getting the contradiction. Okay, so here we can say that is 2 is a common factor of P and Q. Okay, this contradicts our assumption. This contradicts our assumption. Therefore, root 2, which we had assumed as a rational number, and if not rational, then it is definitely irrational number. Okay, so we can write here, therefore 2 is an irrational number, and this was to be proven, so hence proved. Okay, now we'll see next question, question number 2. Here we have second question, which says to prove that 3 plus 2 root 5 is irrational. In this type of question, actually it is not mentioned here, but we have to take this root 5 as irrational. Okay, it is pre-assumed that it is an irrational number, and on the basis of this we'll be proving that this whole 3 plus 2 root 5 is irrational. So let's see how to prove. To prove this, again we use the same contradictory method. So we'll be assuming let 3 plus 2 root 5 is a rational number of the form P by Q. That means we can write P upon Q equals 3 plus 2 root 5. See here, P upon Q, this LHS is a rational number, and in RHS we have these 3 as a rational number, and this 2 is also a rational number, as 3 can be written as 3 upon 1 in the form of P upon Q, where P and Q are integers. This 2 can also be written as 2 upon 1. So this is also a rational number, this is also a rational number, but this root 5 is an irrational number. So what process we follow? We simply transpose all the rational part to any one side. Okay, and we make irrational part of the equation alone in any side, whether it is LHS or RHS. How? Let's see what I am doing here. I'm transposing first this 3 to LHS. So as P upon Q is a rational number, and this 3 when transposed from RHS to LHS, it will be written as minus 3 in LHS. And in RHS we are left with 2 into root 5. Now see, P upon Q is rational, and this 3 is also rational, and this negative is simply finding difference or giving difference of these two rational numbers. So in LHS, this as whole, we have a rational number. Now transpose the remaining, that means this 2 in RHS, which is in RHS, transpose this also to LHS. Okay, and when it will get transposed, it will come in denominator, as here it is in multiplication with root 5. So when it will transpose to LHS, it will go in denominator, so which we can write half into P upon Q minus 3, and in RHS we are left only with the square root of 5. Now, after this, we need some statements. What statements? See, since P upon Q is rational, this is the same which we have assumed, P upon Q is rational, implies that P upon Q minus 3 is rational, because this is giving difference of two rationals, and difference of two rationals is always a rational. And then half, which is also a rational number, is getting multiplied with P upon Q minus 3. Here P upon Q is rational, P upon Q minus 3 is rational, and half is also a rational number. So product of these two will also be a rational number. That means this whole LHS we are getting as a rational number, but in RHS we have an irrational number, and in between these two we have sign of equality. But a rational number can never be equal to an irrational. So that will simply mention here, but a square root of 5 is an irrational, and a rational can never be equal to an irrational. This contradicts, therefore, this contradicts our assumption. And as per our assumption, we had taken 3 plus 2 root 5 as a rational number, and that becomes wrong. So 3 plus 2 root 5 is an irrational. So proved, will at last will write hence proved. Okay, let's see next question, question number 3. Here we have our third question. What it says, prove that the following are irrational. The same type of questions which we have dealt with in question number 1 and 2. In the same way, we'll be solving this also. So we have three sub questions under this question number 3. So we'll be solving one by one. And in the same way, in first, we have to prove that 1 upon root 2 is an irrational number. So here we can proceed in different ways. One way is the same way which we have done in question number 2, but as you have studied in class 9, the rationalization of denominators, so we can use that thing also. In the same way, we'll be simply assuming that this one is a rational number. Okay, just to use contradictory method, let 1 upon root 2 is a rational number of the form P upon Q. That is, P upon Q equals 1 upon root 2. Here we can do one thing. For simplicity, you can use the concept which you have studied in class 9th, and let's do this in next line, not here. Multiply by root 2 upon root 2. Multiplying root 2 in numerator and denominator. So what we are getting here, this concept you have studied in class 9th, rationalization of denominators. In the denominator we have root 2 into root 2, that will become 2. Now as we have discussed in question number 2, simply transpose this 2, which is a rational number, to LHS. So we'll be getting 2 into P upon Q equals root 2. Now you can see that in RHS we are left with only irrational number, okay, which is already proven. This is square root of 2. So after this only the statements are required. We have P upon Q as rational number, that means P upon Q is a rational. So 2 into P upon Q or 2P upon Q is a rational. That means the LHS is rational, but the square root of 2 is an irrational, and a rational can never be equal to an irrational. This contradicts our assumption, and therefore 1 upon root 2 is irrational. So first one is done. What's the second question? The second is 7 root 5. So let's see. In the same way, now I think it becomes very simple to you, and if you have understood, then it's better to try to solve by yourself. Okay, definitely I'm going to give you a solution here, but it will be better if you try by yourself first, and then after come to video and check your answer. So how? First of all, we will be assuming contradiction, that let 7 root 5 is a rational number of the form P upon Q. That is, P upon Q equals 7 root 5. Now simply transpose or do the transposition in such a way that in RHS or in any one of the side, the irrational part becomes alone. So here we'll be transposing this 7 to LHS, so we'll be getting P upon 7Q, and in RHS we are left with a square root of 5 only, okay, which is irrational. Now the statements are required. Since P upon Q is rational, implies that P upon 7 into Q or 7Q is rational, but the RHS, that means root 5, is an irrational, and a rational can never be equal to an irrational. This contradicts our assumption. Therefore, 7 root 5 is irrational. Proved. It was simple. You'll have to try by yourself, practice by yourself. It's very simple. Now let's see the third one. In third, we have 6 plus root 2. Okay, so again we'll be following the same conductivity method. Let 6 plus root 2 is a rational number of the form P upon Q. That means we can write P upon Q equals 6 plus root 2. Now as you can see in RHS we have 6 as rational, root 2 as an irrational. So simply keep root 2 in RHS and transpose this rational 6 to LHS. So we'll be getting P upon Q minus 6 equals root 2. Now statements are required. Since P upon Q is rational, so the difference of two rationals, that is P upon Q and 6, will also a rational number, but root 2 is an irrational, and a rational can never be equal to an irrational. Therefore, 6 plus root 2 is irrational. So we have proved all three, and here we have completed the exercise. So bye for now. Thank you for watching.